Assalamualaikum warahmatullahi wabarakatuh. Hello everyone, my name is Naufal Aulia Amanullah. I am electrical engineering student batch 2019 and today I will present to you about signal propagation and channel models. Okay, first I will explain how the signal propagates in terms of the mathematical models. In telecommunication system, there's a part called as modulation here. The modulation usually modulates the information which is in the binary form from the input. The output of the modulation is an analog signal. The analog signal is in the complex number form. This analog signal is usually amplified or shifted to the frequency carrier. For example, we use Wi-Fi here. In this case, the analog signal will be shifted to the 2.4 GHz and then the signal is transmitted to the antenna. And the transmitted signal that contains information is written in mathematical form as the times e powered by e frequency carrier and t. Okay, and then at the receiver, the signal is written in mathematical form as the y t equal to the ht convolve as the e power of I frequency carrier and t. Okay, the ht is the channel. So the channel is important in wireless communication because any received signal is affected by the channel. Thus, it is essential to know the channel characteristic. Okay, and then propagation characteristic is a factor that we need to know about the signals when we want to transmit them from our transmitter to the receiver. There are several propagation characteristics. Okay, let's take a look at the picture here. An antenna transmitter here, PT, will transmit the signal to the car as the receiver. The first propagation characteristic is the path loss. In the picture here, the path loss is described in blue lines. It means a direct, straightforward path towards the receiver. We characterize the propagation by finding the ratio of the received signal to the transmitted signal over a distance. From this graph, the blue lines represent the path loss. As we can see, there is a very slow change in this ratio. And then the second propagation characteristic is shadowing. Shadowing occurs due to the obstructions from an object. The red block or wall here represent the object. The object affects the signal because it has minor fluctuation, which is different from the blue lines, as you can see here. And then the third one is multipath fading. Multipath fading is the signal that goes to the receiver comes from many different paths or reflections. From the graph, the green line is represent multipath fading. It shows that the fluctuations are more frequent than the red ones. The ratio is not exactly consistently decreasing here. Okay, next is path loss modeling. There are several path loss models. The first one is Maxwell equation. The second one is free space and two path models, and then ray tracing models, then single slope path loss exponent model, and the last one is measurement based and standard models. Signals are consisting of an electromagnetic wave. The first path loss model, which is the Maxwell equation, describes the interaction between the electric field and magnetic field, which is combined together to become an electromagnetic propagation. However, it is quite complex and impractical, so there is a modeling methods that easier to use, which is free space and two-path models. Okay, this is the free space or model and two-ray model. Here's the free space or LOS model. LOS means line of sight model. LOS describes the propagation of the signal without facing any obstruction to the receiver. In general, the free space model characterizes that power falls are proportional to the distance squared inverse. It is proportional to the lambda or wavelength squared and is inversely proportional to the frequency squared caused by the effective aperture of the antenna. And then on the right side, there is two-ray model. In two-ray model, the receiver receives two types of signal, the LOS and the non-LOS signals. The non-LOS signals came from the reflection or refraction. In this model, the power falls is proportional to the distance squared, and the power decreases significantly when the distance is further than its threshold distance. It also states that it is independent of wavelength and the frequency. Okay. The next model is general ray tracing. It takes reflection, scattering, and diffraction phenomena. From the picture here, red lines are the reflection, blue lines are scattering here, and the green line is diffractions. You can see here the green lines. Since there are many reflection or refraction, the receiver may receive many signals. This model requires sight geometry and dielectric properties. Okay, the next model is simplified path loss model. It is the simple version of the path loss model. This model is used when the path loss is dominated by the reflections from the objects. This is the equation that we can use to model the signal propagation. And the parameter that used for this model is gamma or path loss exponent. This path loss exponent or gamma should be within 2 until 8. So dr is the receiver location, and the PR is the power received. D is reference point. To the receiver location, and PT is the power transmitted. Okay. Okay, next one is millimeter wave or mm wave. Okay, mm wave is stands for millimeter wave, is the band of spectrum or frequency bands that lies between 30 GHz and 300 GHz. This is due to the fact that the wavelength of the electromagnetic wave will be in the millimeter range at this frequency range. Millimeter wave is located in the high spectrum bandwidth. Okay, the picture above starts from the top left, which is the lowest frequency spectrum, to the highest frequency spectrum in the bottom right. In the US, the 5G is allocated in the 38 GHz spectrum here. However, currently only a few commercial mm wave systems occupy these frequencies. Millimeter wave still needs more research since its channel models are still immature based on measurements and few accurate analytical models. The path loss proportion to wavelength squared is enormous, and it has oxygen and rain absorption. This picture below shows the power attenuation, which is on the y-axis. Higher power attenuation, it means the worse it becomes. On the x-axis is the frequency. Based on the image, the attenuation is exceptionally high in 6 GHz due to the absorption from oxygen. In other cases, it has spikes when there is a water. Okay, then how to solve the problems that I have mentioned before? The answer is it can be solved by using empirical model. In the area which is not suitable for millimeter wave, the existing channel modeling cannot be used. The early cellular empirical models are based on extensive measurement. For example, the Okumura model, Hata model, COST 231 model, multi-slope model, Wolffish or Bertoni model, and etc. However, the empirical model is dependent on its location. For example, Okumura model that conducted in Japan, where there are many obstructions. Okay, that's all for me. Thank you for your attention and goodbye.